So today's topic is 2-bit binary multiplier. So the concept behind the 2-bit binary multiplier is similar to the multiplication we do in the decimal number systems. Say for example, if you want to multiply 2-bit number which are a decimal number system, say that is 55. If you want to multiply 55 by 15, then what would be the procedure? You will multiply 5 5 to 25, that will give you 5 with a carry 2. 5 5 to 25 again, adding the carry, it will give you 27. Again we're putting the cross over here. 1 into 5 will give you 5. 1 into 5 will give you 5. After multiplication, you need to perform the addition of these numbers. So after adding, you'll get 5, 7, 5, 12, 2 here with a carry 1, 2 plus 5, 7, and adding the carry will give you 8. The total number of sum for multiplying after multiplying 55 into 15 will be 825. That's what we do in normal multiplication. If we talk about the 2-bit binary multiplier, the process will be the same, but we'll do it in the bits form. Say for example, if we are designing 2-bit multiplier, 2-bit binary multiplier, so you need to have two inputs. Let's the two input be A and B. These are the two input. So these will be the inputs for the binary number system, and I'm drawing the block diagram for that. 2-bit will be the input, and one it will be having one output, that will be the product. So this is the block diagram from binary 2-bit binary multiplier. And after that, let us consider an example. Suppose we are having two input A, and if we want to write A into 2-bit, we can write it in the form of A1 and A0. If you want to write B, we can write it in the form of B1 and B0. So A1 is or B1 is the MSB, that is most significant bit. A0 and B0 is LSB, that is least significant bit. Now what do? The next step will be same as we have done in the decimal number system. We'll multiply these two numbers. After multiplication, B0 into A0 will give you A0, B0, A1 into B0, putting the cross. B1 will multiply by A0, that will give you A0 into B1. B1 will multiply by A1, that will give you A1 into B1. After multiplication, we'll add these numbers. After adding, we'll get the sum. For this one, we'll get A0, B0. So I can write here, this can be represented as S0. Sum for this number. A1 plus B0, A1 B0 plus A0 B1. If we add these two numbers, we'll get certain sum, and that sum may be represented by S1, similar to S0. So if in case there is a carry, so that carry out we're getting for this bit C1, that will be the input for the next bit C1. So if in case there is a carry coming out after adding these two numbers, that will go to the other bit, that will be the input for the other bit, and we can add these two numbers again. Then what will the sum for that? That will be carry 1 plus A1 B1. If after adding these two numbers again we get some carry, let's say that is C2, so that C2 will be the input for the next bit. So that C2 will now will come here. If we'll add this C2, we'll get the final output, so that is C3. So we can represent S0, S1, and this number can be represented as S2, and this number can be represented as S3. So as simple as that, the process is same. Now it's time to design the logic diagram for this 2-bit binary multiplier. So in case So in case uh, we want to design this binary multiplier, we have four sum that is in the form of s0, s1, s2 and s3. So for s0, that is nothing but that is the product p0, and that is equals to a0 b0. For s1, that is equal to p1, and p1 is equals to a1 b0 plus a0 b1. s2 is p2, and that's equals to a1 b1 plus carry 1, and s3 is p3, that is equals to c3. So let me remind you, in our previous lecture we have studied about the half adder, which consists of two input and two output. And for the block diagram for half adder is as such. If you want to design 2-bit half adder, we need to require two inputs, that should be 2 bits. Say for example that bits are a and b. After adding these two input, we'll get the sum, and if there is a carry, you get the carry out. So after implementing and designing the K-map, implementing the logic, we have designed that we came to know that for sum, if you want to use the gate, we can use A XOR B gate for designing the sum logic. If you want carry out, we can use AND gate between A and B. So the same concept will apply over here. If you look over here in this term, in the s1, we got two numbers. We are adding two numbers, a1 b0 plus a0 b1. It means if we implement half adder over here, so for half adder we need to have two output. One is for the sum and another one is for the carry. The sum here will be s1 and carry will be c1. So for if we want to draw the logic for sum, we can use XOR gate. If you have to if you want to get the output for carry, we can use the AND gate. Same concept will be applied over here in the second term. In the second as sum, we again adding 2 bit a1 b1 plus carry 1. So that means that a1 b1 and carry 1 are the two input for the next half adder. If this half adder is to be used in this circuit, so again we need to get the two output. One is for the sum, another one is for the carry. So here for the sum again we can use XOR gate, and for the carry we can use AND gate. So so let us design the logic diagram for 2-bit multiplier. So considering this equation for p0, we need to have two input, and that inputs are a0 and b0. And between a0 and b0, we are using the AND gate. We will get the output a0 into b0. That will be the p0. For the second s1, we need another input, that is a1 and b0. a1 b0. We will get a1 b0 from this side. Again a0 b1. b1. So if you see this logic, a1 b0 using AND gate, a0 b1 using AND gate, and there is a addition between two them. So if we use an half adder over here, so for using an half adder we can implement XOR gate for the sum and AND gate for the carry, because after adding two number, if we get a, we'll get definitely get a sum. to obtain that sum, we'll need to have a XOR gate, and for getting an output in terms of carry, we need to fix a AND gate in along with this diagram. So in order to have a sum, we can use XOR gate, and that sum S1 will be termed as P1 over here, and for carry, we can use AND gate, and that carry will be C1. Finally, there is another AND gate of there is two inputs, say A1, B1. That A1 and B1 been provided to the AND gate, and will get the output A1 into B1, and there is another input that is C1, and that C1 is will be coming from this output. So one input from AND gate and one input from C1, so we can use these two input, so we can implement another XOR gate, and that output of the XOR gate will be P2. One input coming from the C1, another input coming from the A1 and B1. This condition is verified. If in case there is an output, there is a carry, then we need to have another AND gate for that carry output, that will be termed as C3, and in that case C3 is nothing but that will be the sum, and that will be considered as P3. So in that case we can verify the we can design this 2-bit binary multiplier logic. And if you want to verify this logic, we can consider an example. Say that example is say, let me erase one these things. Let us consider an example. If we have a equals to 1 1, b equals to 1 and 0. If you want to multiply these numbers, what will be the output? 0 multiplied by 1 will be 0, 0 multiplied by 1 will be 0. Putting the cross, 1 multiplied by 1 will be 1, 1 multiplied by 1 will be 1. After adding this, we'll get 0, 1, 1. That 0 termed as P0, P1, P2. Let's implement this logic in this diagram. Initially, we have these are the two bits A1, A0, B1, B0. Okay, so the value of A1 is 1, the value of B0 is 0. The 1 and 0 will give you the output 0, the P0 will be equals to 0. P0 equals to 0 here, the P0 equals to 0 over here. The value of A1 is 1, so we can write 1 over here. The value of B0 is 0, we can write over here. The output of this AND gate will be equals to 0, and that output of the AND gate is the input to the XOR gate. And the second input for the third AND gate will be A0 value is 1 and B1 value is 1. 1 and 1 will give you the output 1. So the two input to the XOR gate is 0, which is coming from the AND gate second, and one input is coming to the XOR gate is from the AND gate 3. So one input is 0, another input is 1. XOR gate is a odd bit detector. If there is two input which are not equal, the output of the XOR gate will be high, so P1 will be high here. So this concept, this step is also verified. For the third stage, if A1 equals to 1 and B1 is also equals to 1, the output of the AND gate will be equals to 1. The output of the AND gate equals to 1, that output goes to the XOR gate second. This is XOR gate 1, this is XOR gate second, this is AND gate 1, 2, 3, 4, AND gate 5, AND gate 6. So one input to the XOR gate second is 1, and another input to the XOR gate second is coming from the carry 1, which is the output of the AND gate 5. The output of the AND gate 5 is what? One is 0, another one is 1, that is equals to 0. 0 into 1 equals to 0. So now the two input to the XOR gate 2 is 0 and 1. 0 and 1 will give you P2, that will equals to 0. Sorry, that will equals to 1, because if any of the input is high, output of the XOR gate is high. So here we get P2 equals to 1, P2 equals to 1. In case of P3, the one input to the AND gate is 1, another input is 0, the output of P3 is equals to 0. It means there is no P3, no product, the bit will, there will be no output across the P3. So in this case, so this is how we verify the logic. If you have any doubt, you can ask me and in the below comments. Thank you very much.